Welcome to Mathematical Induction. We're going to look at proving results of sums. So firstly, mathematical induction allows us to prove certain types of statements. Normally we are using some of an arithmetic progression or a geometric progression, but we're going to just prove that it works for all values or the set values that are given to us. The following steps are what we follow. So step one, we prove that it's true for n equals 1 or the lowest value of n. So sometimes it'll say n greater than or equal to 0, so you prove it for 0, or it may not work until n greater than or equal to 3, so we'd start at 3. Step two is you assume for n equals k, so you just substitute k for n, and this actually becomes a really important substitution step for step 3, where step 3 we prove true for n equals k plus 1, and then step 4 we just finish with a general sentence saying, hence by the process of mathematical induction we have proven whatever it was we were aiming to prove. So here's an example from a past HSC. We're going to prove that 1 times 3 plus 2 times 4 plus 3 times 5 plus n lots of n plus 2 is equal to n over 6, n plus 1 to n plus 7. So step 1, prove true for n equals 1. So the left-hand side is the first term, so that's 1 times 3, which is 3, and the right-hand side, the sum of that is replacing the n with 1, 1/6 of 1 plus 1 times 2 times 1 plus 7, and that equals to 3. So the left-hand side is equal to the right-hand side. So we have proven that it's true for n equals 1. Assume it's true for n equals k. So remember, we just replace the n with a k on both the left-hand and the right-hand sides. Step 3, prove true for n equals k plus 1. So in step 2, we had the sum of the series on the left-hand side was up to the kth term. So we're now going to add a term, the k plus 1th term, onto the end by replacing k with k plus 1 and having that as a plus, and that'll be our final term. On the right-hand side, we're going to replace k with k plus 1. So notice that on the left-hand side, we've still got all those terms up to k plus 2. Then we add our new terms, adding k plus 1 where the k is. So you get k plus 1, k plus 3. And on the right-hand side, you replace the k's with k plus 1. So we're going to prove that that left-hand side equals to the right-hand side. So we're going to start with the left-hand side and prove. So we're going to start, as I said, left-hand side and prove that it's going to equal to the right-hand side. Notice that that first part on the left-hand side all the way up to k plus 2 is actually equal to k on 6, k plus 1 to k plus 7. So step 2 is a substitution step into step 3. And so that part is what we're going to replace all of that with. So the left-hand side becomes k on 6, k plus 1, 2k plus 7 plus k plus 1, k plus 3. So we want to take the 1/6 out the front. The second term on the left-hand side, the second term doesn't have a 6. So I'm going to recreate it, and you'll see that in green, by creating 1/6 times k. And so what I'm going to take out the front is the 1/6, and I'm going to take the k plus 1. And you'll notice on the right-hand side, that's actually what's out the front, is k plus 1 all over 6, or a 6 lots of k plus 1. And then I'll write what's left inside the brackets. So that's k outside of 2k plus 7 plus 6 outside of k plus 3. So inside that large brackets, we're going to expand, collect like terms, and use PSF to factorise. So we get 2k squared plus 13k plus 18, and the left-hand side is equal to k plus 1 over 6, outside of k plus 2 to k plus 9, which is the right-hand side. So that's true for k plus 1, And step 4 is, hence, by the process of mathematical induction, that proof is has been proven. Thank you.